Hello, continuing from the previous lesson, today we will be continuing on more diversification, more applications of the limit equations that involves the identity of the first principle for you to be able to solve them successfully. So, um, uh, before any more words, I just want to emphasize one thing, that the first principles is defined by first grabbing a point that you want to calculate the instantaneous rate of change from, the instantaneous gradient from, for example, x equals a of the function y equals fx. For you to calculate this instantaneous rate of change, you have to grab an adjacent point, right? An adjacent point and calculate the average rate of change between these 2 points of a and x. However, you move this adjacent point of x comma y fx infinitely closer to a, so that the average rate of change between these two variables will infinitely get closer to the instantaneous rate of change. And since the limit equation signifies the destination in which this equation average rate of change is approaching to, then this equation will exactly be equal to the instantaneous gradient at x equals a, which is also represented in the format or symbol f prime a. However, from our previous lesson, we have learned. However, there is a condition for this first principle to be exactly validly be equal to f prime a, then it must satisfy the two conditions that we discussed over the previous lesson. There are two cases for this limit, in condition that we must satisfy for this limit to exist and be defined into f prime a. First, both limits when h approaches 0 from both the positive and the negative sides should yield the same results for this entire limit to exist and be defined into the form of f prime a. Okay, so that's what we'll take consideration of when solving the limit. So right now we're just discussing about the general characteristics of the first principles. And then the most important thing that we'll discuss is that I want to signify that this whole equation is actually an identity. So basically, there are cases depending on the shape and the appearances of the function. F prime a at x equals a, there are points of a where the function fx will not be differentiable at a, such as like the modulus function. If the vertex of the modulus function y equals fx, if the vertex has the x coordinate a and we want to calculate its average instantaneous rate of change, then since depending on a, the left side of a has a negative gradient and the right side of a has a positive gradient, for example, because of those drastically changing gradient over a critical point, then the limit of the first principles cannot exist. Therefore, f prime a cannot exist on those type of modulus function vertices. So there are cases of, depending on the appearances of the function, that f prime a can exist or not. However, by definition, this limit of the first principles can always be interpreted or can always be defined into a meaning of an instantaneous rate of change at x equals a of the function y equals fx. Therefore, no matter depending whether this f prime a actually exists or not in a function, this limit can always be represented in the form of f prime a. You got it? And you will see why I am emphasizing this identity so much as we go over some of the examples, of the complex limit equations. So there are three most common types of complex limit equations that involves using the identity of the first principles to be able to be solved. However, since the board is too short and I'm pretty sure it's going to consume a lot of time, I'm going to be discussing the 2 out of 3 type patterns of the complex limit equations today on this board. And I'll discuss the latter one, the latest one, the third one on the next lecture. So the next lecture will probably be very short. Okay, so I'm sorry for stalling too long, but right before going into our main concept of discussing the two types of patterns of the complex limit equations, I also want to just emphasize one more thing. This is a tip, so whatever types of complex limit equations that you see, what you always want to do first is you want to artificially make the forms that you are given to the format of the identity of the first principles. So therefore, it is crucial for you to actually genuinely understand this identity's function, its features, and its appearances as well. And therefore, we went over the features that for this first principles to be defined into f prime a, then it must satisfy the limits when h approaches 0 from both the positive and the negative side. So we probably much went over the features of this limit. However, the last thing that we have is the appearance. And why does the appearance matter? Because you can see that h on both the denominator and the numerator has the same coefficient and the same power. So therefore, by studying the appearance here, for the first principles to be defined into f prime a, then not only it must satisfy the both limits when h is approaching from both 0 from the positive and the negative side, but it must also satisfy the case in which the h has the h on both the denominator and the numerator must contain the same coefficients and also the same order of power. So those are the two conditions that we must make while trying to tailor the equation that we are given, tailor the complex equation that we're given into the format of the first principles. So now let's begin by analyzing the first pattern. The first pattern is usually given in a case like this. And I will give the general thing that f prime a, in this case, I'll just put it in a premise or supposition that this is equal to 5. F prime a, if it exists, is equal to 5. Okay, and you were told to solve this limit equation. What kind of value will you get? Well, let's first analyze this. So we both have the case when h is approaching 0 from both the positive and the negative side. Okay, and the h squared, yeah, they're the same. So although they have the power of 2, but they're still, the denominator and the numerator still has the same coefficient, same order of power. So by the definition, can't it literally just be represented in the form of the first principle, just like f prime a? Because the endpoints, what we're trying to find the instantaneous rate of change from here is also a, as you can see from both a's here. Well, it could be, so however we're not sure, right? This is just an approximation based on the appearances that is have. However, while we said that h must approach 0 from both the positive and the negative side, I actually forgot to mention here, but you can see that h here, both the denominator and numerator, you can also see that this h shares the same h as here. So basically what I'm trying to say here, the denominator and the numerator here is not h with the power of 1. However, it has the power of 2. So therefore, since these all three h's had a power of 1, so we must try to, for us to basically tailor this equation to the identity formula of the first principles, then we must also change this h into a format of h squared. For these three factors to be all considered the same, and for this equation to be considered the genuine identity of the first principles. So let's say that we try to tailor this h into h squared. Then, if this h squared can approach 0 in both positive and the negative direction, then we will be able to see that this, if we are given the proof that if h squared also approaches 0 from both the positive and the negative side, then we can say that this equation can be representing the same identity of the first principle, thus can be represented in f prime a, which is 5. However, we want to prove that it can both approach 0 from the positive and the negative side, or it might yield a different value. So let's search it up right now. So first, what we're trying to do is, well, since we do not know how this power of 2 will affect this limit, this is too complex, like, first to see. Like, we've always seen the power of 1, but now we're seeing the power of 2. So since it is too complex, we don't know the implications or the effects that this power of 2 will bring to this limit range here. So therefore, let's try to use the process of substitution. So let's try to substitute this into an artificial variable of t, which in this case, if we substitute h squared into a value of t, then we will be able to have a variable with the single coefficient, with coefficient of 1 and also the power of 1, which is more akin to the identity of the first principles, right? So And then if I substitute t into a form of h squared, then this can be represented into the format of as limit. Since I don't know what the variable t will approach, I will leave this blank for a while. T a plus h squared will be substituted into t and fa. So this is more akin to the form of the first principles, right? So then, since I have h also, just like the denominator and numerator, I'll also have t here for it to be represented in an exact identity of the first principle. For then, I will need to know what value t actually approaches to. And if we were given the proof if t approaches 0 from both the positive and the negative side, then this is literally the same as the identity of the first principle. Then it will be able to be written in the format of f prime a. However, we do not know this yet. I'm sorry for the repetition, I keep repeating, but this will be the last time. So, since t is equal to h squared, the value in which h squared is approaching to as h approaches 0 from both the positive and the negative side will also be the value in which t is approaching to. So, first, when h is... So, there can be also two cases, when h approaches 0 and when the h approaches 0 from the positive and the negative side. So, then we will see how the h squared changes as h approaches 0 from both the positive and the negative side. And the values in which h squared approaches as h approaches 0 from positive and the negative side, both limits will be considered into the values in which t or h squared will be approaching to. First, so how do we consider this limit? We first have to draw a function that represents it. So, let's consider this as a function, h squared as a function. And you will see the reason why I'm doing this as soon as I draw it. So, and then I'll draw the function. Okay, so I have a parabola function of y equals h squared. So, now you get to understand why. H can approach 0 from both positive and the negative side. And since this function signifies the y value of h squared, you will be able to be geometrically or vividly able to see what the h squared approaches to as h approaches 0 from both the positive and the negative side. Because this is h squared and this is the y value. So when h approaches 0 from the positive side, then for us to know what h squared is approaching to, we just have to look on what this function's y value is approaching to, because this signifies h squared. So you can see as h approaches 0 from the positive side, the h squared, y equals h squared, is also approaching 0, right? This is getting bigger to smaller. However, is it becoming 0 from the positive side or the negative side? Yeah, it started off from big and continuously got smaller. So basically, h squared is becoming also 0 from the positive side as h approaches 0 from the positive side. And now when h approaches 0 from the negative side, then we also see the same case that h squared is approaching 0 from the positive side as well. So, while considering the two conditions when h is approaching 0 from both the positive and the negative side, we also see that h squared, also t, also same as t, is also approaching 0, however, only from the positive side, not the negative side. So, we can say that t, or h squared, is approaching 0, however, it is not approaching 0 from both the positive and the negative side, however, only approaching 0 from the positive side, as shown from the red function here, which signifies h squared or t. So, we are able to write that it only approaches 0 from the positive side. And what the hell is this? We said from the identity of the first principles that for this identity to be represented in a format of f prime a, then it must satisfy the instantaneous rate of change when h approaches 0 from both the positive and the negative side. However, this equation only considers when t or h, whatever the variable, approaches 0 from the positive side. So therefore, if we try to demonstrate, let's say I want to calculate the instantaneous rate of change at x equals 0, like x equals a, let's say a is at 0 of this function y equals fx, then Well, you initially have to grab x from both the positive and the negative side of A, and then you have to calculate the instantaneous rate of change to see that they are equal, right? However, you're not considering the negative case here. You're only considering the case when x approaches A from the positive side. So therefore, well, you're going to have, although it looks very similar in definition or in identity or in mathematical characteristics, you're going to achieve two very different type of equations, although it looks very, very similar to each other. So therefore, what is the value? What is this value? So in general, well, we said that f prime A is equal to 5. However, fortunately, we are able to calculate this value directly because for f prime A to be converging into a fixed value of 5, then the limit when h approaches 0 from the positive and the negative side should be equal to each other. So this implies that the limit when h approaches 0 from the positive side is also 5, and the limit when h is approaching 0 from the negative side is also 5. So therefore, since we are only asking about the question in which the t is approaching 0 from the positive side, and we are trying to find the instantaneous rate of change of that at x equals a of the function y equals fx, then since when h approaches 0 from the both positive and the negative side, the value is 5, then this value will also be equal to 5. However, it will not be able to be distinguished or be written in the definition of f prime a, because f prime a considers the limit from both when h approaches 0 from the positive and the negative side, but this equation only considered when h approaches 0 or t approaches 0 from the positive side. So you will be able to see the reason why I emphasize the identity of the first principles so much in the beginning of this lecture. So we discussed the first pattern here. However, let's generalize this a little bit. Let's say that I want to calculate the limit a similar format. However, now it is not h squared, but it is now h cubed. What will this result in? What will this result in? So I'll just emphasize one more time that this cannot be f prime a. Okay. Got it, right? Okay, so in this case, what do you think that this represents? Well, let's try to use the same format. First, looking at the appearances here, well, both the denominator and the numerator features have the same appearance as h cubed. However, the limit here is not in h cubed. So for this equation to be tailored into the actual identity of the first principles, then we also need to tailor this into a form of h cubed, right? However, rather than doing that, let's just use the process of substitution to generally just artificially bring this equation more smoothly into terms of when t approaches something. So if it is a little difficult to understand, first these h's were first in a form of the power of 1. So since the cubic is kind of a little complex to us, let's use the process of substitution to make this artificially into terms, substitute this artificially into terms of a variable with a coefficient of, with a power of 1. So just like the first case, first question here, let's use the variable t is equal to h cubed. And then, if we represent it here again, I don't know what t will approach to as h approaches 0 from both the positive and the negative side. So I'll leave this for a second. And h squared will be a t, so it will be same equation from above as above, a plus t minus fa. However, I want to know what, if I want to tailor this into a terms of first principles, then I also need, as these both the denominator and the numerators are both t with the power of 1 and coefficient of 1, then this t must also have a power of 1. So therefore, what does t approach to? Well, then we have to use the same case as we did from above. We want to see as h approaches 0, h in this case can both approach 0 from positive and the negative side, right? So we want to see what t approaches, what h cubed approaches as h approaches 0 from both the positive and the negative side. If t can approach 0 from both the positive and the negative side, then this will be tailored exactly congruent to the identity of the first principles. In that case, it will be able to be represented into the format of f prime a. However, since we are unsure, let's try it right now by artificially drawing a function to geometrically check if our speculation or if our assumption is true or not. So, do you guys know how to draw a cubic function of x cubed? Well, I do. Well, x cubed actually has an appearance like this. That was a horrible drawing, but still, sorry. It looks like this. So this is the function y equals x cubed. Well, h cubed, sorry. So we want to consider what this function, also equal to t, approaches to as h approaches 0 from both the positive and the negative side. So let's consider the cases one by one. When h approaches 0 from the positive side, then the h squared is actually starts off from the very positive infinite side. However, when h approaches 0 from the positive side, this function representing the h cube converges to 0, however, comes down from the positive side. So therefore, when h approaches 0 from the positive side, h cubed equal to t, t also approaches 0 from the positive side. However, when h approaches 0 from the negative side this time, you can see that this cubic function from the negative side of 0, starts off with the negative infinity. However, gets slightly less negative to become 0 as h approaches 0 from the negative side. So therefore, since it gets bigger actually, we can say that this function approaches 0 from the negative side. So we are looking at what h cubed t approaches to, right? So you can see that as h approaches 0 from both the positive and the negative side, shown on a horizontal line, the vertical line that we're looking for also approaches 0 from both the positive and the negative side. So therefore, we are able to write that t, or h cubed, is approaching to 0 from both the positive and the negative side, which can be simplified into just t approaches 0 here. Then, what does this imply? Well, we are able to see that this equation is congruent exactly with this identity of the first principle. So that is why, surprisingly, even though this power of 2, h with the power of 2, did not share the same mathematical identity and characteristics as the first principle did, this one is exactly equal to the identity of the first principle. So this equation, we can say, this equation is exactly equal. This equation is exactly equal to the first principle identity, which is f prime a, which is also equal to 5. So while these values contain the same value, same answer of 5, you will need to understand, you should be able to understand that these share a whole different mathematical characteristics and properties. So let's try to generalize this a little bit. If I go this up to the 4th power of h, 5th power of h, and so on forever, you are going to see a distinct pattern here. Whatever you do, you are going to try to draw a function in which what the substituted value of t approaches to when h, when you begin with, approaches 0 from the both positive and the negative side. So therefore, we saw on when the power was even, when h approached 0 from both the positive and the negative side, then h squared or t that you substituted h squared into approached only 0 from the positive side. Well, you can see from this, when you square a certain number, even a negative value, you are only able to get a range from that is same or bigger than 0. However, by looking at the odd power here, for example, h cubed, which was substituted into t for easier representation into the identity of the first principles, when h approaches 0 from both the positive and the negative side, h squared or t both approaches 0 from positive and the negative side, which you can get this ideology from h squared. When a negative is cubed, when a negative number is cubed, then it results in a negative number. However, when a positive number is cubed, then it can have it will have a positive number. So it is free to have both negative and positive number. Its range both occurs all the real numbers. So therefore it can approach 0 from both positive and also the negative side. I just showed you in a visual function by drawing a function which was pretty tedious because I wanted to get you to actually understand the close processes on how the proving was done for what t approaches to when h approaches 0 from both the positive and the negative side. But by thinking of this ideology that I talked about, that a number h with a power of an even number can only have a range that is same or bigger than 0. So therefore it is only able to approach 0 from the positive side when h approaches 0 from both the positive and the negative side. However, when h has a power of an odd number, then since the odd number powers can have all the ranges from positive and negative, then when h approaches 0 from the positive and the negative side, then the h with the infinite odd power can approach 0 from not only the positive side, like the even number power, but also from the negative side. So, from this ideology, what you can get is, let's say that h is like 252. Then what will you be able to get? Since this is an odd power, when h approaches 0 from the both positive and the negative side, h 252 second power will only able to approach 0 from the positive side. So therefore this will only result in, when t, by having an instantaneous rate of change when h approaches 0 when this value approaches 0 from the positive side. However, when, let's say this is like 35, it's an odd number, right? Since h to the 35th power can approach 0 from both the positive and the negative side because it has an odd power, then it means that it's substituted h. When we substitute this into t, then t can also approach 0 in both ranges of positive and the negative side of 0. Therefore, it is what do you call it? It concords directly. It is basically symmetrical to the form of the identity of the first principles. So you are going to be able to define this into terms of f prime a. Okay, so that was a pretty long first pattern. Now let's briefly go over the second pattern. I'm pretty sure that this pattern will be a little shorter than the first pattern. So the second pattern that we will be looking at is when limit approach h 0. Now let's consider the case when h and f a plus 5h minus fa. And by the way, the same f prime a equals 5 applies to these patterns as well. Well, that's just the premise that I made, that f prime a is 5. What applied here also applies here. Consider this as the same function fx. So, imagine that this equation, you were given this equation in an assessment and you were given to solve this. Well, okay, this looks confusing, but still what you have to remember first, try to always tailor this equation into an identity, or an identity in the form of the first principles. So what do? Well, obviously we saw that the denominator and the numerator h must be exactly identical to each other in a factor of coefficient and also the order of power. So therefore, both has an order of power of 1. However, this one does not have a 5, and this one does not have a 1. So those coefficients differ, right, by 1 and a 5. So we have two options. We can either make this 1, or we can either make this 5, right, in terms of appearances. However, I want to emphasize that changing this value 5 in a function, it is surrounded by a function y equals fx. So therefore, this entire value is very hard to manipulate. Since this overall value must always stay the same, if you want to manipulate this variable, it is very difficult to do while trying to keep this equation the same. So it is actually more easier to convert the denominator than the numerator, which is surrounded by a function. So what I'm trying to say is, it is way easier to artificially make this 1h into 5h then convert 5h, which is surrounded in the function y equals fx, to a plus h. So then let's try to convert this into 5h. Well, what do we do then? First, I'm going to tell you a very, very egoistic or very stupid approach. First, I'll write the numerator here. So I want to make 5h for the denominator and the numerator h should, to have the same coefficients, right? Then just write it. First. However, there must be no resultant stimuli or no resultant change in this overall equation. This equation must always stay the same. So therefore, since we artificially added 5, then we must eliminate the 5. Therefore, we will artificially multiply it by 5 so that by viewing this in entirety, then this equation will have no overall change from this initial equation that we were given. However, if we separate this, we are able to represent this into a closer form of the first principles. So, also, since this limit has no correlation or no effect from this limit because it does not have a variable of h, we can send it from out here. So we are able to say it is 5 times limit this equation. However, we also need to say that this h is not in concordance with the 5h. However, we said if h needs to, well, by looking at the identity of the first principles, h must approach both the 0 from the positive and the negative side. So therefore, if the substituted h, if the 5h, or when you substitute it into a variable of t, if t approaches both 0 from the positive and the negative side, when h approaches 0 from the positive and the negative side, then you will be able to represent this into a form of the first principle because it corresponds to the exact identity of the first principle. So, well, let's say that, I'm just going to show you one more time. Let's say that t is 5h, and then when h approaches 0 from both the positive and the negative side, what does t approach to? What does 5h approach to? Well, 5 literally has no affection here because it is not a variable, but it is a constant. So therefore, t and both 5h will approach 0 from both the positive and the negative side when h approaches 0 from the positive and the negative side. So that is why when you have it both all in a linear equation and a constant is multiplied here, well, you really don't need to use the complex process of substitution like you did when we had a difference in the power of h, order of power of h. So when you're actually dealing with the sort of a question, type of a question that is a different coefficient of h, then just forget about it. Like it doesn't really matter anyways. Because this 5 doesn't have any characteristics that will alter the value in which t will approach to as h approaches 0 from both the positive and the negative side. T's range, 5h's range is same. The value in which t or 5h approach to is same as the value in which h is approaching to from both positive and the negative side. Since they are able to have the same value of which they are approaching to, well, if you want to substitute it so much, then when t approaches 0, you'll again be able to put this into a form of equation. I'm getting bored now, bro. And you can see this concords exactly to the identity of the first principles. Same t coefficient in order of power on both the denominator and the numerator. Same value of t is approaching to the t is in the same format as the t on both the denominator and the numerator inside the limit. So therefore, since it concords directly to the property of the first principles, then we can confidently say that this is f prime a. However, we forgot the 5 here, right? We forgot the 5 that we multiplied this to cancel out the equation to make it same as the initial equation we were given. So we will have 5 f prime a. And since f prime a I said was 25, then 5 times 5 will be equal to 25. Okay. However, okay, that was a really good question. However, we have a different case. Well, you don't expect this h to be always 1. Either of these coefficients to be always 1. That would be too easy. What if they all had a different number that differs from each other and neither of them are 1? Then let's consider another case. when, let's try the case when limit h approaches 0, and this is 3h, and we're trying to find the equation of 7h minus fa. So you can directly see that these coefficients, well, they have the h's on both the denominator and the numerator has the same order of power, however, shares the different coefficients. However, you're still able to realize that this is somewhat related to the identity of the first principles because they both share a, and they look similar in the format, right? So how are we going to alternate this? How are we going to bring this tailor this into a form of the identity of the first principles? Let's look at the appearances. Well, we have the 7h and the 3h, and I have two options: to make the 7h into a 3h, to make these two coefficients equal, or otherwise manipulate the denominator 3 here, artificially make this into a 7 so that these values will be the same as 7. So make this into 3 or make this into a 7 to make these equal. However, from above, manipulating what is inside the function is very difficult to do. So therefore, a relatively easier way is to just manipulate the denominator that is independent of any functions, or any parentheses, or any composites that we know of. So let's artificially make this into a term of 7. 7h. Let's just write that. I know it. I'm very brave, you know. This is a very valiant thing to do. However, I want to cancel this out. And it's going to be a little more difficult than the previous one. Since this was 1, we did not really need to consider. We just had to cancel out the denominator because the denominator was already 1. However, this time, the denominator originally had a coefficient of 3. So therefore, if we cancel this equation out to cancel everything out so that it goes back to normal to the initial equation that we were given, then since this 7 didn't exist here at all in the first place, we will have to cancel it out. And what was originally there was 3. So we have to add 3 here so that when 7 is simplified, then 3 will just go into the place of the coefficient of the denominator, coefficient of h, so that everything will be equal to the initial equation, so that no external changes made to the overall equation. So therefore, since this 7/3 does not include any variable of h, it has no relation to this limit after all. So we are able to bring this directly out into outside 7/3 multiplied by limit this. However, applying the same convention, applying the same tradition here that we did, that when we were trying to substitute this in terms of 7, when 7h approaches 0, or substitute 7h in terms of t to see what t approaches when h approaches 0 from both the positive and the negative side, we said that since h is an odd number power, and since constant 7 does not have any impact of determining, altering the range, altering the values in which, altering the signs in which h is approaching 0 or not, we can just say, we don't really need to use the process of substitution here. Without actually making the 7, we are just able to know that this thing literally coincides with the identity of the first principles. Because 7h, as h approaches 0 from both the positive and the negative side, 7h also approaches 0 from both the positive and the negative side. And if you are unsure, you will just be able to find this out by drawing a linear function that represents 7h here, a linear equation. And as h approaches 0 from both the positive and the negative side, just by showing you guys one more time, you'll be able to know that this function, this red line here, which represents 7h, will also approach 0 from both the positive and the negative side. So therefore, there's really no point. 7 really has no impact. Even if this is like 100, even if it's not a 7 but 100 or 1000, it's still going to be yielding the same results of both approaching 0 from the positive and the negative side. So applying the convention that whatever variable can approach both the 0 from the positive and the negative side when they have an order of power of an odd number, we can literally confidently say that this equation here is congruent directly to both in an appearance and a featuring way. They are exactly equal to what the identity of the first principles denote. So therefore this is exactly equal to f prime a. However, 7 over 3 is multiplied. So therefore it is 7 over 3 f prime a, which is equal to, since f prime a is 5, then it will be 35 over 3. Great job. And just like we did, this is literally the last thing that we will do for this lesson. Since we made a generalization for this, depending on whether h had an order of power of positive or a negative number, we can also make a generalization for this equation here. Let's consider the case. Limit h approaches 0 from both positive and negative side. Let's not do a since we already have a. Let's do bh and fa plus ch minus fa. You are going to be able to see for this format that when denominator h had a 5, coefficient of h had a 5, and the numerator coefficient of h had a 1, then we just have 5 f prime a, which is calculated by 5 over 1. Right? So we can say that this is equal to 5 over 1, which concords to the coefficient of h from the denominator and coefficient divided by the coefficient of h from the numerator. And from the second equation here, we had a 7 as a coefficient of h from the denominator, and the 3 for the coefficient of h on the denominator and this on the numerator. However, we were also given the value of 7 over 3 f prime a, which 7 divided by 3 also corresponds to the 7 divided by 3. So the coefficient of h of the numerator divided by the coefficient of h on the denominator. So applying the same convention as we did to two of the examples that we did here, by applying the concept that first writing the f prime a, and then writing the convention by dividing it by the numerator and the denominator coefficient of h's, so it will be 3 over b. We are able to get the general equation for this particular concept of complex limit questions. So these are the general concepts. These two patterns are the general patterns and the general concepts that is actually represented, that usually or frequently, sporadically comes out as the applied, more diversified forms of complex limit that utilize your understanding and of both the identity of the first principles and the concepts of the limits on the continuities for you to tackle on successfully. And we only covered the two of the patterns today. However, we'll be covering the latter, the third one, which will probably take the most time to cover between the three typical patterns. So since we covered the majority today, the next lecture will just cover on the latter concept, which is a little more complex than these two patterns. However, I'm pretty sure that we will be able to tackle it on successfully, just like the convention that we applied for today, by using both the concepts of the limit identity of the first principles and also the continuity and the basic limits. So by applying those two key concepts that I shared from the beginning of the lesson, which I deemed very significant by solving these questions, by using those same conventions, we will be able to tackle them successfully on our probably most notorious equation, the third pattern as well. Thank you.